They told us 3. I-Atlas was discovered on July 1st, 2025. That is a lie. TESS saw it 2 months earlier. 64 days before astronomers announced the third interstellar visitor racing through our solar system, this satellite built to find alien worlds caught something else entirely. An object so faint it should have been invisible, moving too fast to be one of ours. And when scientists finally stacked over 9,000 images to see what TESS captured, they found dust behaving in a way that breaks every model we have for how comets work. The dust was moving at less than 10 meters per second. That is the speed of a bicycle. Normal comet dust flies at 20 to 100 meters per second. This stuff was crawling. So slow that it never formed the extended coma that screams comet activity. The object looked bare, dead, but it was not dead. It was leaking material so gently, so impossibly slow, that TESS could not see the cloud forming around it. Only the brightness gave it away. The point source was too bright for a bare rock. Something was there, wrapped tight around the nucleus, dust ejected with such minimal energy that it hugged the surface like atmosphere on a planet. This changes everything we thought we understood about 3I Atlas. Because if the dust was that slow in May, when it was 6.4 astronomical units from the sun, it means this comet was active in conditions that should have left it frozen solid. Carbon dioxide ice should barely sublimate at that distance. Water ice stays locked. Yet, TESS brightness measurements from May 7th to June 2nd show an object already glowing, already surrounded by material, already defying the physics we use to predict comet behavior. The TESS magnitude readings hit Tmag equals 20.83 plus or minus 0.05 and 19.28 plus or minus 0.05 across 2 camera observations. That brightness at that distance meant coma, but where was it? If you value documented space exploration history like this, subscribe. It is the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the American Astronomical Society paper published in Research Notes of the AAS in October 2025 by Martinez Palomera and colleagues, and from IOP Science peer-reviewed findings on TESS precovery observations archived at ARXIV preprints 2508.0, 2499, and 2507.21967. Both published in August 2025, with data validation cross-checked against Hubble Space Telescope findings. Now back to the information. 3I Atlas entered our solar system at 58 kilometers per second relative to the Sun. That is 209,000 kilometers per hour, faster than any confirmed interstellar object before it. 1I Oumuamua hit 26 kilometers per second. 2I Borisov reached 32. This thing came in at nearly double Borisov's speed. That velocity tells a story. Objects do not reach those speeds by accident. Every close pass by a star adds momentum. Every gravitational slingshot through dense stellar neighborhoods ratchets up the velocity. The faster you move, the longer you have been traveling. The longer you have been traveling, the older you are. Multiple research teams ran the calculations. Hopkins and colleagues at Oxford published findings in July 2025, suggesting 3I Atlas is between 3 and 11 billion years old based on its out-of-plane velocity and speed through the galactic thick disk. Taylor and Silliman at Cornell arrived at similar age ranges using different age-velocity dispersion models. Perez Kudo's team at the University of A Coruña traced the comet's orbital history back 10 million years through the Milky Way using Gaia mission data. Their backward integration showed that despite multiple close stellar encounters, the comet's overwhelming velocity kept it on course. It crossed the galaxy like a bullet, unperturbed, ancient, 10 billion years. That is what the numbers suggest. Older than Earth, older than the Sun. Older than the solar system itself by more than 5 billion years. A relic from when the Milky Way was young and the universe was less than 4 billion years old. Formed in an era astronomers call cosmic noon, when star formation peaked and planetary systems were building at rates 10 times higher than today. The Atlas survey in Rio Hurtado, Chile, spotted it on July 1st, when it was 4.5 astronomical units from the Sun. The Minor Planet Center received 122 observations from 31 observatories within hours. By July 2nd, David Jewett and Jane Liu confirmed it was clearly active using the Nordic Optical Telescope. Miguel Alarcon's team at Teide Observatory found the same. But the critical clue came from Quanji Ye at the University of Maryland, who dug into Zwicky Transient Facility archives and pulled pre-discovery images from June 28th and 29th. That extended the observation window from 3 hours to 3 days, enough to calculate the orbit. Hyperbolic, unbound, interstellar. Then someone checked TESS, The transiting exoplanet survey satellite was never designed to hunt comets. It watches stars, looking for planets crossing in front of them, blocking their light. But during its extended mission, TESS pivoted to observe the ecliptic plane for 10 non-consecutive sectors. Sector 92 ran from May 7th to June 2nd, 2025. And 3I Atlas happened to pass directly through that field. The object was too faint to show up in individual 200-second exposures. So researchers Adina Feinstein, John Noonan, and Daryl Seligman used a shift stack method. They corrected for the comet's motion across the detector, aligned over 9,000 frames, and co-added them into 2 deep stacks. 1 from camera, 2 CCD, 3 covering 10.9 days. 1 from camera, 1 CCD, 2 spanning 14.7 days. Total observation time, 26 days, and there it was. A point source. No extended tail, no visible coma spreading outward. Martinez Palomera's independent team ran the same process and arrived at matching conclusions. They performed aperture photometry and pixel response function photometry on the stacked images. 15 measurements total, with signal-to-noise ratio above 3. The PRF light curve showed gradual brightening from Tmag 19.57 plus or minus 0.15 as the comet approached the inner solar system. Expected behavior. But when they measured the radial profile, comparing 3I Atlas to 4 asteroids with similar proper motion, they found something shocking. The profiles were comparable to inactive objects, no extended coma. That should mean the comet was dead, bare nucleus, no activity. But the brightness contradicted that. Cross-referenced with Hubble observations from July 21st, the magnitude showed clear coma contribution. Dust and gas surrounding the nucleus, scattering sunlight, boosting the brightness beyond what a bare rock could produce. So there was coma. TESS just could not see it spread out. The paper's conclusion landed like a hammer. If activity was sustained for any significant length of time, the dust in the coma must have been ejected at very low velocities, less than 10 meters per second. Anything faster would have created an extended envelope visible in the stacked images. Anything normal would have shown up. This did not, because the dust was moving so slowly, it never escaped the central point spread function. Bryce Boland's team at Palomar measured dust ejection using July 3rd observations with the 200-inch telescope. They analyzed the sunward extent of the coma and constrained particle speeds. Micrometer scale to millimeter scale grains, 0.01 to 1 meter per second. That is not a typo. 1 meter per second. Walking speed. Boland's paper, published in Astrobiology in July 2025, calculated the dust mass loss rate at 0.1 to 1 kilogram per second, based on those velocities. Compare that to normal comets. Hubble data from July 21st showed that by then, small 1 micrometer dust grains were leaving at 22 meters per second, large 100 micrometer grains at 2 meters per second. Still slow for the large grains, but the small ones had finally ramped up. Avi Loeb's analysis in August 2025 calculated a total mass loss rate of 10 kilograms per second, using ram pressure models and rotation constraints. The comet was producing 6 kilograms per second of small dust and 60 kilograms per second of large dust by late July, according to Hubble measurements from Jewett's team. But back in May, out at 6.4 astronomical units, it was barely dribbling material into space. Submeter per second velocities. Why? Carbon dioxide. The JWST observations on August 6th by Cordner and team found a carbon dioxide-dominated coma. CO2 production rate, 129, plus or minus 1 kilogram per second. Water, 6.6 plus or minus 0.2 kilograms per second. Carbon monoxide, 14 plus or minus 0.9 kilograms per second. The CO 2 to water ratio hit 7.6 plus or minus 0.3, among the highest ever measured in any comet, 4.5 sigma above the trend line for long period and Jupiter family comets. Carbon dioxide sublimits at much lower temperatures than water. At 6.4 astronomical units in May, CO2 ice could start turning into gas. But water stays frozen until closer to 3 astronomical units. That explains early activity, but it does not explain the ultra-slow dust. CO2 jets on normal comets create high-speed outflows. They accelerate dust particles to escape velocity. They blow material away from the nucleus fast. 3I Atlas was not doing that in May. It was leaking. One explanation, the nucleus structure. If 3I Atlas is a pristine sample from 10 billion years ago, its ices may be amorphous, disordered. Formed in the cold outer regions of a protoplanetary disk around an ancient thick disk star. Amorphous ice has a different structure than crystalline ice. It holds volatile molecules trapped in its matrix. When it warms, it does not sublimate cleanly. It releases gas slowly, diffusively. Without the explosive jets that create high-speed dust emission, JWST detected water ice grains smaller than 1 micrometer in the coma. Not water vapor, ice grains. That means chunks of ice were being lifted off the surface without fully sublimating first, passive ejection. Drag from escaping CO to gas, gently pulling ice fragments along. Not high-pressure jets, just steady seepage. The ice grains stayed cold enough that they sublimated later, hundreds to thousands of kilometers from the nucleus. Swift Observatory detected hydroxyl radicals on July 31st and August 1st, suggesting water vapor was forming at distances between 4,000 and 10,000 kilometers from the nucleus. Extended sublimation zone. Ice grains drifting outward, slowly warming. Finally turning to gas. That would produce exactly what TESS saw. Dust and ice moving so slowly they never formed an extended envelope. Brightness from scattered light off material clinging close to the nucleus. A compact cloud that looked like a point source in the telescope. Activity without obvious coma. But here is where it gets strange. By late July, 3, I-Atlas had developed a sunward fan. Hubble images showed a teardrop-shaped dust plume pointing toward the sun, not away from it. Normal comet tails point away because solar radiation pressure blows small particles back. 3, I-Atlas had that tail too, faint, broad, pointing east away from the sun, but the dominant feature was the fan going the other direction, toward the sun. Jewett's Hubble analysis, published in Astrophysical Journal Letters in August 2025, explained it. The sunward fan is anisotropic ejection from the day side of the nucleus. The sun heats one hemisphere, ice sublimates faster there. Gas flow accelerates dust preferentially in that direction. Perpendicular velocities measured at 7.5 times beta to the 1/2 meters per second. Parallel velocities higher. The dust cones out in a fan with opening angle determined by the velocity ratio. Too heavy to be blown back by radiation pressure, moving slowly enough that it falls toward the sun instead of streaming away. By September 14th, the James Clerk Maxwell Telescope measured hydrogen cyanide production at 4.5 plus or minus 1.9 times 10 to the 25th molecules per second, 2 kilograms per second of cyanide. The cyanide coma stretched 180,000 kilometers across, asymmetric, elongated in the anti-solar direction. The dust tail by then reached 50 arcseconds, 100,000 kilometers long. But in May, none of that existed, just a faint point source, slowly leaking material at walking speed. TESS captured 3 I-Atlas in its earliest observable activity phase, before Hubble, before JWST, before any telescope pointed at it deliberately. 26 days of continuous monitoring at a distance where most comets are dead rocks, and it found an object already awake, already active, already showing that the models need revision. The implications go beyond one comet. If 3 I-Atlas can be active at 6.4 astronomical units with ultra-slow dust, other interstellar objects might be doing the same. Passing through undetected because their comas are too compact to register as extended sources. TESS would have missed 3 I-Atlas entirely if it was any fainter. The magnitude was right at the detection threshold for stacked images, slightly dimmer, slightly farther away, and it vanishes. How many have we missed? The number density calculations from interstellar object studies suggest we should see more of these. Marchetta and Seligman's 2023 paper on synthetic detections with Vera Rubin Observatory predicted the legacy survey of space and time would find dozens once it begins full operations. Hopkins, model from the Otautahi-Oxford framework, estimates 50 interstellar objects detectable by Rubin over the survey lifetime, some as large as 3 I-Atlas, some older. 3 I-Atlas reaches perihelion on October 30th, 2025, at 1.36 astronomical units. Just inside Mars' orbit, it will pass Mars on October 3rd at 50 million kilometers distance, ExoMars. Trace Gas Orbiter and Mars Express will attempt observations using CASIS and HRSC cameras and multiple spectrometers. The comet stays visible until late November when it passes behind the Sun. Europa Clipper and JUICE spacecraft will attempt coordinated ultraviolet observations. Then it leaves, heading back out into interstellar space at 58 kilometers per second. By December 31st, 2026, it will be 13.93 astronomical units away. Magnitude, 27 to 34.7. Fading, by 2027, 26.27 astronomical units. Magnitude 29.7 to 37.4. Gone. We will not see it again. No telescope can track it past 2027 unless something dramatic happens. Outburst, fragmentation. Unlikely but possible. More likely, it fades into the background. becoming another invisible traveler in the galaxy, carrying its 10-billion-year-old ices back into the dark. But TESS gave us something permanent, the earliest confirmed observation of an interstellar comet showing activity. Proof that these objects can be active far beyond the distances we thought possible. Evidence that dust ejection at sub-10 meter per second velocities is real. Data showing that compact comas can mimic inactive nuclei if you do not stack deep enough. 26 days of photometry that extends our understanding of 3I Atlas back 2 months before discovery. And a lesson in what we miss. TESS was not looking for comets. It was watching stars. The observation was serendipitous. Sector 92 happened to cover the right patch of sky at the right time because TESS had been reoriented during its extended mission to survey the ecliptic plane. If that pivot had not happened, if Sector 92 had targeted a different region, TESS would have no data on 3I Atlas. We would know nothing about May activity, nothing about the ultra-slow dust, nothing about how far out the comet woke up. Vera Rubin Observatory would have discovered 3I Atlas before Atlas did if its science validation had started 2 weeks earlier. The observatory was being tested. Calibrated. Not yet scanning for real. 2 weeks. That is how close we came to missing priority on the discovery. Atlas got it on July 1st. Vera Rubin looked at archived images and found 3I on June 21st, 10 days earlier, but those images were not checked in real time. TESS saw it on May 7th, 55 days before Atlas, 64 days before anyone knew it existed. But TESS does not check for moving objects in real time either. You have to look back, dig through archives, stack thousands of frames. We are flying partially blind. Most sky surveys scan once and move on. Objects moving fast across the field get 1 or 2 frames. Not enough to build a light curve, not enough to see extended features. You need multiple exposures, hours of stacking, processing power, algorithms that can shift stack for non-sidereal motion. Most surveys do not have that. TESS does because exoplanet hunters developed those tools for different reasons. They needed to track spacecraft wobble, correct for scattered light, pull signal from noise. Those same tools let researchers recover. 3I Atlas from May data, months after the fact. The age estimate keeps settling around 10 billion years. Multiple independent methods converge. Age-velocity dispersion relations point to 3 to 11 billion. Thick disk origin models say 7 to 10 billion. Backward orbital integration through 10 million years of galactic history shows no major trajectory changes, despite close stellar encounters. That level of velocity preservation over that timescale means the object has been moving fast for most of its existence. Fast enough to avoid capture by any star it passed. Fast enough to maintain course through the densest parts of the spiral arms. Fast enough to survive billions of years in interstellar space without being slowed, captured, or destroyed. If it is 10 billion years old, 3I Atlas formed when the universe was 3.8 billion years old, before the Sun, before Earth, before the solar system. It formed around a star in the galactic thick disk, a region where only 10 to 15% of the Milky Way's stellar mass resides. Stars there are ancient, metal poor, formed during an era when the galaxy was still settling. Thick disk stars have higher velocity dispersions because they formed in a more chaotic environment. More mergers, more scattering events, more gravitational kicks that sent objects flying. Somewhere in that thick disk, a protoplanetary disk formed around a young star. Carbon dioxide ice condensed in the outer regions. Water ice mixed in. Organic compounds irradiated by the star's light formed tholins, red carbon-rich molecules that coat the grains. The disk built planetesimals. Some grew into planets, some stayed small, comets, icy bodies. Scattered by the growing planets during system formation, flung outward, ejected, sent into interstellar space with enough velocity to never return. 3I Atlas tumbled through the galaxy. Passing star systems, molecular clouds, nebulae, each encounter added momentum. Gravitational slingshots from stars boosted the speed. After billions of years, the velocity reached 58 kilometers per second, fast enough that even when passing stars got close, their gravity could not bend the comet's path significantly. Perez-Kuto's simulations show that over the past 10 million years, 3I Atlas experienced multiple close encounters with stars. None changed its course substantially. The comet just kept going, straight through, unperturbed, until it reached us, our solar system. The sun's gravity well bent the trajectory into a hyperbolic path. Closest approach, 1.36 astronomical units. It swings around, picks up speed, and leaves. The visit lasts months, then it is gone, back into interstellar space, carrying its ancient ices back to the thick disk. Or maybe it keeps going, 58 kilometers per second is fast enough to leave the Milky Way's disk entirely, escape into the halo, the void between galaxies. We got lucky. TESS happened to be watching. Atlas happened to catch it in time for follow-up. Hubble and JWST had time to schedule observations. Ground telescopes around the world coordinated campaigns. Dozens of papers published before perihelion, spectroscopy, photometry, orbit refinement, composition analysis, age estimates, origin modeling, all from one object, one visitor, the third of its kind. But the TESS data remains the most puzzling. Ultra-slow dust at 6.4 astronomical units, activity without extended coma, brightness without obvious explanation, dust moving at walking speed when it should fly. The answer might lie in the nucleus structure, amorphous ice, extended sublimation zones, CO2 domination, ancient composition from a thick disk star. All of those factors combine to create behavior we have never seen before. Because we have never studied a 10 billion year old comet before. 2, I, Borisov, was maybe 1 billion years old, similar to the Sun, similar to the solar system, normal comet behavior. 3, I, Atlas, is 10 times older, from a different era, different chemistry, different formation conditions, different everything. Of course it behaves differently. The question is, how different? The answer lives in data no one will collect because the opportunity passed. TESS stopped observing that field in early June. By the time anyone realized the comet was there, Sector 92 was over. TESS moved on. Other fields, other stars, other science. The 26 days from May 7th to June 2nd are the only TESS data that exist. No follow-up, no confirmation. Just those 9,000 frames stacked into 2 deep images showing a point source that should not be that bright at that distance with that little extended coma. Future missions will change this. Vera Rubin Observatory begins full operation soon. It will scan the entire southern sky every few nights. Anything moving will get multiple detections. Light curves will build automatically. Objects that appear as point sources in single frames will reveal extended features in stacked images. The survey will find interstellar objects early. While they are still distant, before they get bright, before anyone realizes they are special, Rubin might find 50 interstellar objects over 10 years. Some will be asteroids, rocky bodies, dead, no volatiles, no coma. Some will be comets like Borisov, active, normal behavior. Some will be like 3I Atlas, ancient, unusual, challenging our models. And some will be things we have not imagined yet, faster, older, stranger. Each one is a message from another star system, a sample of planet formation from a different time, a different place, a different chemistry. We cannot send probes to other stars. The distances are too vast, the travel times too long, but other stars send their debris to us, ejected planetesimals, failed planets, scattered comets. They drift through the galaxy, billions of them, most invisible. Too small, too dark, too far. But occasionally one passes close enough to the sun that we can see it, study it, measure it, before it leaves forever. 3, I Atlas will not return. Its trajectory is unbound, hyperbolic, escape velocity. Once it leaves the solar system, it heads back into interstellar space at 58 kilometers per second relative to the sun. Add the sun's motion through the galaxy, and the comet's galactic velocity is even higher. It will never be captured by another star unless it hits something. Odds of collision, negligible. Space is empty. Even in dense star clusters, the distances between objects are enormous. 3, I Atlas will drift for another billion years, maybe longer, until the galaxy itself changes shape, until the Milky Way merges with Andromeda in 4 billion years. Even then, the comet might survive. Too small to be affected by the chaos, just another piece of debris in a cosmic cloud. But we saw it. For a few months. From May to late 2025, TESS caught the earliest phase. Walking speed dust, compact coma, invisible activity. Atlas found it in July. Hubble showed the sunward fan. JWST measured CO2 dominance. Ground telescopes tracked composition, rotation, color evolution. Mars orbiters will image it in October. Deep space probes will try for distant observations in November. Then it fades, drops below detection limits, becomes a catalog entry, a data set, a collection of papers. And somewhere in those papers, buried in supplementary tables, lives the TESS photometry. 15 data points, T magnitudes, timestamps, heliocentric distances, showing an interstellar comet at 6.4 astronomical units, ejecting dust at less than 10 meters per second. The only direct measurement of that phase, the only proof it happened, found by accident, recovered from archives. Published in Research Notes of the American Astronomical Society in October 2025. 3 pages, 1 figure, minimal discussion, maximum impact, because now we know interstellar comets can be active far beyond normal limits. Dust can move at walking speed. Comas can be invisible. And if we want to find these objects early while they are still distant, we need deep stacks, shift stack methods, algorithms that hunt for faint moving sources, surveys that revisit fields, time domain astronomy applied to solar system science. TESS proved it works, not on purpose, by accident, but it works. The next generation of sky surveys will do it deliberately. Rubin, NEO surveyor. Others, they will find interstellar objects before they get bright, before the coma develops fully, while they are still cold, still leaking material at sub 10 meter per second velocities. And when they do, we will be ready, because 3I Atlas taught us what to look for. Ultra-slow dust around an ancient visitor from the galactic thick disk, 10 billion years old, moving at 58 kilometers per second, ejecting carbon dioxide and dust at walking speed when it should be frozen solid, defying models, breaking predictions, forcing revisions. That is what TESS found, 2 months before anyone else, hidden in 9,000 frames, waiting for someone to stack the images and look. The data sits in archives now, public, available, processed. Anyone can download it, check the numbers, verify the claims, run their own analysis. That is science, open, repeatable, built on evidence. 3I Atlas keeps moving. 1.36 astronomical units at perihelion on October 30th. Then outbound. Past Mars, past Jupiter in March 2026, past the asteroid belt, past the ice giants, past the Kuiper belt, into interstellar space by 2027. Beyond all but the most powerful telescopes. Into the dark, carrying its 10 billion year old ice, its CO2 coma, its ancient tholins, its story. And TESS keeps watching. Different fields now, different stars, looking for planets, finding transits, building light curves. Not looking for comets, but if another one drifts through sector coverage, the data will be there, waiting, ready to stack, ready to reveal, because that is how discovery works now. Not just dedicated surveys, not just targeted observations, but archival data, reprocessed, reanalyzed, stacked in new ways, shift-corrected for motion, calibrated with modern techniques. Every survey becomes a time machine, every observation a potential discovery decades later when someone looks again with better tools. TESS saw 3I Atlas, 55 days before, Atlas. But we only know that now, months after discovery, because researchers went back, checked the archives, found the data, stacked the frames, measured the brightness, compared to models, published the findings. The comet was there all along, moving through Sector 92. Too faint to see in single frames, too fast to trigger automatic alerts, but visible, detectable, measurable. If you know where to look, if you stack deep enough, if you check the archives, how many others are hiding there? In test data, in Gaia scans, in Hubble calibration frames. In JWST engineering tests, how many faint-moving objects drift through background images, never triggering detections, never flagged as anomalies, just sitting in archives waiting for someone to notice? The answer, we do not know. But 3. Atlas proves they are there. Ultra-slow dust reveals their presence if you look carefully. Compact comas show up in brightness measurements even when they do not extend visibly. Ancient visitors from distant star systems pass through our fields of view. Most invisible, some barely detectable, a few just bright enough. If you stack, if you correct, if you care to look, and we looked, TESS delivered. Martinez Palomera, Tucson, Hedges, and team extracted the signal. Feinstein, Noonan, and Seligman confirmed it independently. Both groups arrived at the same conclusion: ultra-slow dust. Less than 10 meters per second, walking speed. Around the third interstellar object, 2 months before discovery, captured by a satellite built to find planets, found by scientists who refused to assume the archives were empty. That is the real discovery, not the comet itself, but the method, the proof that you can find these objects early if you try, that precovery observations exist, that archives contain gold, that ultra-slow dust is detectable even when comas are invisible, that interstellar visitors announce themselves faintly, far in advance. If anyone is listening, TESS was listening, accidentally, for different reasons, but listening. And it heard walking speed dust around a 10 billion year old visitor from the galactic thick disk, racing through our solar system at 58 kilometers per second. ejecting material so gently it never formed an extended envelope. Glowing faintly at magnitude 20, 6.4 astronomical units from the Sun, on May 7th, 2025, 55 days before anyone knew its name. We left 3I Atlas in the late summer of 2025, us, a 10 billion year old enigma leaking dust at walking speed. Its secrets were locked in amorphous ice, a relic from a star that died before our sun was born. The data from TESS gave us a glimpse of its bizarre, gentle awakening far from the sun, but that was just the beginning. The real test was always going to be the fire, the final, perilous plunge toward perihelion. As August bled into September, the comet crossed a critical threshold, 3 astronomical units from the sun, the frost line. Here, for the first time in perhaps billions of years, solar radiation was intense enough to sublimate water ice. The gentle seeping of carbon dioxide, which had defined its early activity, was about to be overpowered by a far more violent engine, and the ancient visitor began to scream. Ground-based telescopes reported the change almost overnight. The comet's brightness surged by 2 full magnitudes in less than 48 hours. The compact, tightly bound coma that had fooled TESS into seeing a bare rock exploded outward. The dust velocities, once measured at less than 10 meters per second, were now clocked at over 500. The walking speed dust was gone, replaced by a storm. The water engine had ignited, and it was ripping the surface apart. This was not the clean, predictable sublimation we see in comets from our own solar system. This was chaotic. The light curve became erratic, jumping and plunging as new vents of pristine, 10 billion year old ice were exposed to sunlight for the first time. Each flash was a pocket of trapped gas, frozen since the Milky Way was young, finally bursting free. Spectrometers detected not just water, but a rich soup of complex organic molecules: methane, ethane, and faint, tentative traces of glycine, the simplest amino acid. It was the chemistry of a different time, a different place, preserved in a deep freeze and now being broadcast across our solar system. Then came the 3rd of October, the Mars encounter. As 3I Atlas flew past the red planet at a distance of 50 million kilometers, our orbital probes turned to watch. The ExoMars Trace Gas Orbiter's CASIS camera, designed to map minerals on the Martian surface, captured a series of staggering images. It did not just see a fuzzy coma. For the first time, we resolved structure. Not the nucleus itself, it was still too small and shrouded, but multiple distinct jets of material erupting from it. They were not firing randomly. They were synchronized, pulsing in a complex rhythm that betrayed the comet's rotation. The data suggested a day just 4.7 hours long and a spin axis tilted almost 90 degrees. It was tumbling through space on its side, one pole baking in constant sunlight. This explained the sunward fan Hubble had seen earlier. The extreme axial tilt meant the day side was always pointed sunward, creating a continuous, focused outflow of dust and gas too heavy for solar radiation to push back. It was a fire hose of ancient material, aimed directly into the solar wind. Now, with perihelion just 2 weeks away, the chaos is escalating. The primary jet, erupting from the sun-baked pole, has begun to splinter. High-resolution observations from the Very Large Telescope show it twisting, corkscrewing into a spiral. The nucleus is precessing, wobbling like a dying top. The immense torque from the violent, asymmetric outgassing is physically twisting the comet in space. Its ancient structure, stable for eons in the frozen dark, cannot handle the stress. It is tearing itself apart from the inside out. The question that every astronomer is asking is no longer what this comet is made of, but whether it will survive. Will it hold together as it whips around the sun on October 30th? Or will the final, most intense blast of solar heat trigger a catastrophic failure? Fragmentation, a complete structural collapse that turns this unique messenger from the past into a cloud of dust and ice. If it disintegrates, the show will be spectacular. A temporary, brilliant smudge in our sky as 10 billion years of history vaporizes in an instant. But the scientific loss would be immeasurable. If it survives, it will fly back out into the void, scarred and forever changed. But carrying with it the secrets of its passage. It will have proven that some relics from the dawn of the galaxy are tough enough to endure the fire. In 14 days, we will have our answer. The telescopes of Earth are waiting. Every instrument that can be pointed at it is... We are watching a messenger from cosmic noon face its final trial, a trial by fire, to see if the oldest things in the galaxy are also the strongest.